and we have quickly come to almost the end of this program. That is, today is the last day of this program. So we started from Monday onwards, and today is the last day for this program. So, and coming to today's talk, so it will be on the biomedical applications. So, as we know that this technology has a lot of potential that you might have experienced during these 4 days. And one among the potential areas of this additive manufacturing is medical application. So undoubtedly, this technology is going to play a vital role in biomedical application. The reasons, as you are already aware, that 3D printing is very well there. The presence of 3D printing wherever you have the complexity of the product. So human anatomy is going to be the most complex geometries. So you have a lot of neurovascularity and you have a lot of free-form anatomy. And not only the complexity and the driving force of this medical application of 3D printing is customization, personalization. So we need to oftenly go for patient-specific or patient-matched implants. So this technology is very well known for delivering the solutions for customization and personalization of the devices, medical devices or the implants. So that is specific and that is unique to the patient required anatomy. So that is going to be the key point of this 3D printing, why it is so popular in biomedical application is. And the presentation outline goes like this. So I'm going to discuss the case studies so that we have performed along with our collaborators in the area of cranioplasty, dental, and as well as oral maxillofacial. So these are the three medical specializations. So we have worked with the hospital people to solve a certain complex surgical treatments normally they come across. So how this has been integrated this technology with the surgeons, especially to perform a complex surgical procedures by making use of 3D printing technology. So, and during my talk, so I'm going to discuss the 6 case studies so that we have performed along with our collaborators. And before I start, these case studies, so we quickly introduce this technology, the medical 3D printing technology, and then we'll discuss one by one these 6 case studies and the future direction, of course. So you have a lot of scope to even print the organs. But the scope of organ printing or bioprinting is at the very beginning, even some extent it has been realized maybe simple organs like skin or blood vessels, bladder also people has been successfully printed and it has been implanted into the human bodies. But still it has to go long way to go. Why? Because one day may come that you can see the complete functional organ is getting printed through this technology. Maybe down the lane, 10-15 years, maybe you can expect such kind of development. But let me say, give you this the state of art of this organ printing also at the end. So this is what I have planned for this session. And let us quickly introduce this medical 3D printing technology. This we have already given a bit of introduction in the design aspect of 3D printing. So where we need to start with the medical image processing data in any, say, medical application of 3D printing, it should start with the digital data. So where do you get the digital data? But again, with the advent of computers, so you have say tremendous development in say medical imaging. So where you before the computers and after the computers. So previously we used to have only X-ray say technology to capture the cross-sectional images. So that too in a two-dimensional, and that too it will be at a time you can take only one cross section and you don't have any digital backup. I'm talking about the before the computers, maybe during late 60s and early 70s. So then computers has changed a lot. So as we know that nowadays you have a CT, MRI images that you can say capture the cross sections at several say levels, and then you can say get several images, so hundreds of images. So as for your say tissue of interest, maybe bone, maybe a soft tissue, so you have a different scanning modality to pick your region of interest, or to pick your say organ of interest, or to pick your tissue of interest. So then you have all these technologies. So then you can start your journey by say scanning the patient at the region of interest, and scanning the patient at the region of interest so may not be sufficient to say integrate your this medical data to 3D printing technology. So it should be further processed in a medical image processing software. So ultimately your aim is to say segregate your tissues. Means say you might have taken a chest CT of a COVID patient. So she or she wants to say know the score or the level of infection that the COVID patient is having. So in that case, so your region of interest will be the lungs, but you may not be interested at this point of time knowing about the ribs or the spine, or maybe another tissues, other tissues which it consists of. But so definitely you are interested to say the lungs is your region of interest for to know the score of the COVID patient, say infection levels. So then your region of interest is say lungs, and then by making use of these medical image processing softwares, so you can pick the region of interest. So in this case, this is the lungs, and then further this virtual model so has been saved into an STL or AMF, 3MF, or any 3D printer recognizable format, so that we can say save that data in this medical image processing software. So your journey of 3D printing in medicine will start with, say, acquiring the images by an appropriate scanning modality, and then it has been, say, segmented by using certain tools like segmentation and using region growing and other tools. Then you may be able to pick your region of interest, and you may be able to say reconstruct the images into a 3D virtual model, and further it should be recognizable by the 3D printing technology. So 3D printing machine, the recognizable format. So you are comfortably able to say generate that. So once you generate that, so of course you may back and forth take this data to the CAD system or FEA or CFD, or you do simulations on this, say the data of the patient, which you might have created some, say, customized implant for the pelvic joint, or somewhere where you are looking at to say designing customized implant for the patient specific thing, then you can say do that. So, and even you can generate a 3D computer model, and then you do a design validation. So you perform certain say inspection or verification, design validation verification will be done. So nowadays there are these softwares are certified by the FDA or any other regulator to integrating this say practice in a regular say surgical procedure. So then you have a certain clearances also. People are nowadays able to get these validations can be done. Now you have a certain standards or certifications qualifications so given by the regulators to adopting this practice in the regular the we can even further say print these models which were virtual model. Further it has been converted into a physical 3D model by using the 3D printing technology. So that is quite apt. Why? Because you have a several complexity, undercut, lot of undercuts, and vascularity in a typical human anatomy. So that can easily done through this 3D printing technology, as we already understood for the past 4 days of this FTP. So you have this data has been processed by making use of any one of these softwares. So then you are say your application lies say in several folds. Say some of the say cases which we need to say back and forth go to the CAD system and simulation, as I already said, or computer models or FEM or CFD. So for orthopedics, so then you may obviously go with FE analysis, or for a cardiac people, then you may oftenly go to a CFD analysis to analyze the blood flow and so on. So you oftenly say migrate, or you need to go to different platforms. So from your medical image source data to any one of these say tools or the softwares or the applications where you need to migrate it. So then which we need to familiar about these tools, and then we can very well adopt this technology in the say in the healthcare say applications. And of course we have several softwares to do this job. Even you may already aware. So you have the mimic software, 3D doctor, simpleware, and other proprietary softwares, and the open source software. Here is a 3D slicer, is the one which you can download as a free of cost, and then you can say use this technology, the software to integrate means DICOM images. Normally, you start with taking a DICOM image. So that is the de facto standard in the say digital medical imaging. So any say scanner or any medical scanning modality will give you to allow you to save your data, your images into a DICOM images. So that DICOM images, so you say import to any one of these softwares, maybe proprietary, maybe open source. So just you can import these images, and then you perform all these say operations or by making use of those tools. So you can very well pick your region of interest. So and then further can say transport this or you can import this data say as for your application demand. Sometimes so IGS format is needed, and sometimes if you are looking at 3D printing, obviously you may go with the .stl file. So just you convert your DICOM images into an STL file. So that is very well done through this kind of open source softwares. So that's going to be the starting point of your say medical image processing, and further getting ready to integrate with the 3D printing technology. So that definitely we need to have a certain software tool to interface directly. You cannot take the DICOM images and sending it to the 3D printer. So though both works with the sliced data or the cross-sectional data, but unfortunately you don't have any mechanism to directly recognizing your DICOM images by the 3D printer. Obviously, you may require this sort of software tool to integrate your data to 3D printing machine. So once you have say comfortably done this, and then why you are looking for a physical model. So though you have let's say virtual models and talking about the virtual simulation tools, you have let's say virtual reality, augmented reality, and say you have a lot of developments in the say sort of computer technology or the computer graphics or the computer technology. You have several developments, but still a physical model is a physical model. Nothing will be beat by the physical model. Why? Because as we know that you have a physical feel and touch and feel kind of a thing once you have a physical model. So then that too, you can very well say communicate to the say different surgical teams so that are involved in a typical surgery. For example, consider this model. So this model um, is meant for designing a customized implant for the facial reconstruction. So here, so obviously a oral maxillofacial surgeon is involved, and here, so you have an orbital position here, and eyeball should be kept in a right place. Otherwise, there will be a chance of losing the vision of the patient vision. So in that case, like your ophthalmologist is also part of this surgery. So like that, so the several say specialized surgeons are involved in a single surgery. So then definitely, if you are having a physical model like this, and you design an implant and you have the patient data, and then further it has been printed through using a 3D printing technology, and it's a matter of hours. Maybe you can quickly print it. So maybe within one day, you are able to process the data, you are able to print it, and you can deliver this to the surgeon and surgical teams. So let them plan the surgery. Say like it is a better communication tool once you have physical model with you, and not only among the surgical teams, and even you can very well educate the patient. So what you are going to do say you can very well educate the patient on say showing these physical models to him or to her, so you can have a better communication among the surgical teams and the patient. And it also assists the surgeons with a diagnostic purpose and the surgical planning purpose. Like say, based on this, so they can very well plan the surgery well before the actual surgery they are going to say perform in the operation theater. Even they can take these models to operation theater and they can intraoperatively work on this. So you can sterilize these models, so then you can take it into the operation theater and say that sort of say um, the freedom that the surgeon is having. Say he can very well plan the surgery and what sort of surgical instruments he has to carry, and the surgical say devices sometimes you can plan based on, or some template is needed to assist the during the surgical procedure. Like say, then you can design a template or a guide, so based on the patient say requirement, so then you can even supply that sort of devices um, so to the surgeon, and then they can very well plan this, and they can even rehearse the surgery on these models, and they can come out with the best surgical procedure never been before. Why? Because they can have an opportunity here to come out with an innovative surgical procedure. So because of this patient condition, so it's already say known by the surgeon, so it will make the things simpler rather than so trying out in the operation theater. But before that, well planned surgery, and say the outcome of the surgery, and the precision levels of the surgery, all it, it will be improved because of these physical models. Otherwise, they may be, say, relying on the images, the computer images, and of course, based on their skill and the experience, normally they can, yeah, do it. But definitely, this sort of technologies will enhance even it is a disruption. Even a junior doctor may also know. So definitely experience is experience, but they will definitely here you have an opportunity in terms of the technology, so they can then have a better say planning the surgery and rehearsal the surgery and simulation of the surgery, so they can very well do on these models, and even they can create a customized prosthesis. So this is the another say benefit in terms of physical model once they are able to build it. Uh, Say somebody has to have some artificial limb, so that artificial limb um, so that will say depends on the patient to patient so then you can customize say artificial limb or ears or nose or anywhere, so where you can even say customized uh, required or custom required prosthetics can be designed, fabricated, and it has been say fitted to the patient. That is another advantage. By making use of this, can very well design, fabricate, and fit a customized prosthetics to the patient. And even you can accurately place the implant. So you have designed an implant. So for example, this is very much very crucial, the orbital rim here, and then you have this implant and the fitment of this, how exactly you are able to fit this. So that is going to change your vision of the patient, and even so the facial say appearance and that sort will say help the patient to correctly place this implant. So once you have these models, so like this we can talk about several benefits or why you are needed a physical model why can't you manage with a virtual model or a computer model? So definitely you have all these benefits once you have a physical model with you. And this is the general procedure, any medical 3D printing, say process. So we already understood that it should start with the CT, MRI, or any other, say, medical data. It has been acquired from the patient anatomy, and it has been two-dimensional cross sections, and further it has been reconstructed based on your region of interest. So then you are able to reconstruct this 3D model, and that too in STL file or any 3D printer recognizable format. And now onwards, you know that say we need to say do a design for a 3D printing. So that is you fix the orientation and you generate the supports, and then you say supply all the process parameters to the machine. So then you are able to generate a cross-sectional data or a layered data. Those layers has been sent to the machine, and inside the machine, so where the physical realization of these models so has been done from the bottom to top. So then exactly the model or the anatomy or the organ or whatever the thing that you have captured here, and it is getting fabricated here. Let it be a skull or let it be a limb, artificial limb, which you are trying to, and you have a reverse engineering technology also that's going to play a vital role whenever you're working with an artificial, say, limbs or any sort of prosthetics that you're going to work. So definitely your application is going to be say in several folds. So then how you are going to make use of this model that has been fabricated through 3D printing technology. So you can use it in several folds. Now you have say organ printing and the bioprinting as evolving. So in that case, the material is going to play a vital role, right? Say so right now we are talking about all these skull or the bones. So these are the predominantly these are the say you are going to have a man-made or a synthetic material that you are replacing these say tissues, but again, these are the man-made material or synthetic materials. But if we talk about the organ printing, so the material is totally different here. It's going to be the blood cells or the living cells of the own patient. It is getting extracted, and then it is getting, say, cultivated in the incubator, and further it has been multiplied, and then ultimately again it is putting back into the patient body. So then there will be several challenges in order to say implement this organ printing as such. But anyway, you have here a lot of scope to work on that, but material is going to play a vital role here. So though you have the technologies, and why this material is so important means there will be a stringent requirement for the say biomaterial you call normally. So the material should have biocompatibility, and material should have say, certain properties which it is on par with the native organ or a tissue. So then how it is possible can the material scientist can say make these materials, and then you have a stringent requirements for these materials, right? So you cannot say use all the engineering materials as the biomaterials. Why? Because we'll try to see, we'll try to define what is a biomaterial and what is the importance of biomaterial. Say, to see the definition of the biomaterial, so the biomaterial is the synthetic material used to replace to restore the function, so to a body tissue, and it may be continuously or intermittently in contact with the body fluid. So this is going to be, say, a synthetic material or a man-made material, which it is continuously contacting with the body fluid. So means you have to have the first characteristic is the first and foremost, it should be a biocompatible. Means what do you mean by biocompatibility? It should not, elicit any kind of adverse reactions from the body or vice versa. So it should not even a toxic. It should be a non-toxic, and it should be non, say, carcinogenic. Means it should not create any a kind of cancerous kind of thing to the human, say. So then, which it requires definitely this stringent requirement of biocompatibility. So majority of the engineering materials are getting eliminated to being used as a bio applications. So then you're reducing the options with you. So among the, say, you have engineering materials, maybe 10 to 10 to 15% maybe the qualified maybe for the biomaterials. You have a limited choices, and that too if you come to 3D printing, whether all that 15% materials that are available, can it be 3D printable? So then again, where you will be losing other options as far as 3D printing is concerned. So as engineering materials, majority are not qualified for bio applications, and further, some of them are getting eliminated because of printability through the 3D printing technology. So, and of course, not only the biocompatibility, your biomaterials should also have adequate physical and the mechanical properties. It should, say, on par with your, say, native bone or whatever tissue you are targeting it, you want to replace it. But definitely it should have physical and mechanical properties on par with that body tissue that you are targeting to replace or supplement by using this biomaterial. So, and practically use of this biomaterial should be, it should be amicably formed. That means easily it should be, say, machined, or easily it should be 3D printable. Now we are talking about 3D printing. It should be, say, easily 3D printable, and it should more economical. So it should not, say, put more cost for the production of these biomaterials. So it should be more economical, and it is readily available. So these are if you talk about practical situation of biomaterials, so it should satisfy this. So because of these requirements, maybe you may have a very limited choices of materials that it should be done. And ideally, your biomaterial should have the following properties, like, say you should have the biocompatible and chemical composition to avoid any adverse tissue reactions. And it should have excellent resistance to degradation. If that is made out of, say, metal, it should be, say, more corrosive in nature, and it is a polymer, say, so it should have a biologically, say, resistance towards degradation of the polymer. So if it is made out of a biopolymer, and it should have that, say, property, and it should have the acceptable strength to, say, sustain the cyclic loading by the joints, especially if you talk about orthopedicians. So definitely you need to have these subjecting to joints or subjecting to cyclic loading. So those cyclic loadings this material is able to, say, withstand without failure. And also it should have a low modulus to minimize the bone resorptions, and it should have high wear resistance to minimize the wear debris that has been generated. So like that, you have several properties, the characteristics or the properties of these biomaterials it should so satisfy. If somebody is interested, you can further refer this handbook of materials regarding this biomaterials. So then, okay, this is about the biomaterials. Then one can understand the importance of the materials. So then coming to 3D printing, can all the polymers, the biopolymers can be printed? Yeah, maybe you can have the extrusion based systems, or even you can have a certain um, say VAT based systems can also be capable of printing these biopolymers. Like say if you see the biopolymers, so right from the say head to the toe, so you can find in several places how these biopolymers, say right from the polyethylene to polypropylene, PET and polyamide and other say group of these poly groups. So you have even including hydrogels. So you have these applications. So in terms of the ear parts or the facial prosthetics, or even you have say everywhere. So you can even make use of these for the replacement or some sort of say lungs or kidney and the liver parts can also be heart pacemakers. Even you can make use of the material, these biopolymers, and you can have sutures. You can make use of our finger joints or blood vessels, knee joints, bones and joints. So you have the applications of these biopolymers in the human, say, body. So in several fold, and then you can use an appropriate material for an appropriate, say, application. Say ear and ear parts. You have certainly a good number of choices here to go with. Say ear or ear parts, dentures. Also, you have several options to go with, and facial prosthetics, PVC based thing, and you have everywhere. Say heart, lung, blood vessels, bone joints, knee joints. You have an appropriate say biopolymer that can be used for your applications. So coming to 3D printing, yes, you can even print majority of these materials through the otherwise, if you are not able to done through directly these materials, even you can go with the secondary process of say casting, or you can make a mold and then further you can replicate it by any one of these material that you are targeting at. Why? Because if your facility that you have, it is not able to directly manufacture any one of these materials, and then go with the secondary process, like so you prepare a mold or impression, and then get it casted or get it impression of that through the secondary process. So you can say comfortably print these biopolymers in majority of the 3D printing technologies. And coming to biometals and alloys, so you have say 316L is one of the stainless steel say steel alloy that you can make use of say fracture fixation stents and surgical instruments. And you have several say titanium, say, alloys. So titanium, commercially pure titanium, aluminum, vanadium, and you have several compositions or the alloys of the titanium alloy. You have a lot of scope to have here, and then you have bone and joint replacement, fracture fixation, dental implants, pacemakers, and other applications you may be using it. And cobalt chrome is another. Say whatever I mentioned here, that is easily done through 3D printing process. I mentioned only those materials here. So the cobalt chrome, you have bone and joint replacement, dental implants and dental restorations, and heart valves. And nickel titanium, you have bone plates, stents, orthodontic wires, and gold alloys for dental restorations, silver products, so antibacterial agents, and platinum electrodes. And then you have amalgams. So you have a combination of different materials can also be having this dental restoration purposes. So you can even I may be missing some other materials. Even these are these the well-known materials that you can easily done on any of your 3D printing technologies. But even you can develop your own material also, that is always there. But then you ensure that it has been certified by the regulator that you are going to use this for implantation purpose, especially if you're using a permanent implant or a thing that is going to be sometimes, not all the times you may use as a implant. So sometimes you may use as a device or the template. So in that case, we not bother about much. Whenever you have this implant, so that is going inside the human body, then only we need to say follow, and then you have several challenges in that. And you have bioceramics and glasses, so aluminum for joint replacement, dental implants, zirconia for again joint replacement, calcium phosphate for bone repair and augmentation and surface coating on the metals. Also, calcium phosphate will be used, and bioactive glasses for bone replacement, and porcelain for dental restorations, and carbons, hot valves, and dental implants. These are some of the bioceramics and glasses. And biocomposites also can be used for the dental restorations, the silicon fillers as glass fillers with the polymer like PMMA and other things for the dental applications. So these are the composites, biocomposites, so that can done through 3D printing process. So then, okay, then you have say the materials. We have discussed the how do you create say a file to be ready for the 3D printing, and further the material. So these are the design and the material. So these are the two things is very much needed for any 3D printing application. And of course, medical, we need to think about the biocompatibility and other considerations and the things which we need to make use of these. So if you see in broad medical applications, like it may be the implantation application, like if you see the companies like Anatomic, Zimmers, or Stryker. So these are the well-known medical device manufacturers across the globe. So they are say looking for this 3D printing solutions. So either for the say chest implant that has been made through titanium material, or even it could be a spinal wedge or a spinal cage or everywhere. So the reason, as we already know, that we can biomimic the patient condition or the patient structure. So you have a bone, and again, bone is a combination of say solid somewhere and porous somewhere. So means it's a combination of say a cortical and trabecular kind of a structure. A bone this consists of, and then that how you are going to mimic the bone structure. So that is always with your modeling techniques, lattice-based designing, and then to integrate this with the 3D printing technology. So exactly you are going to biomimic the structure of the patient. So that is you may be having a certain porosity of these bone structures. So then you can very well mimic that kind of structure into this in terms of this implant, and that's the advantage why people are looking for this kind of solutions for 3D printing in medicine. So that is the implantation purpose. But even you can very well use this models for the planning the surgery. So, for example, you have a pediatric heart surgeon. So the pediatric heart surgeon, so it's a challenge for him to operate a month's baby or a day's baby to be operated. So then that's going to be very complex surgery or very sensitive surgery rather than. So then they have to operate on that. Nowadays, you have the FDA approvals for the clearances for the sort of softwares or the sort of materials or the sort of products as such. So then you can very well use these models for planning the any sensitive surgeries like this. So you can very well plan this by printing these models. And even orthopedic casts, so like you can have the advantage as when we discussed in the design for 3D printing aspects, like say you can have the lightweighted structures or the bionic designs or a lattice based structures So that is very well supported by 3D printing technology. So that is very much needed for an orthopedic. So when orthopedic or aerospace application also, it's the same thing, like where you may be looking for a lightweight structures to minimize the say payload. And here also we're very much needed the similar lattice or a bionic or a topology or a lattice based structure basically. This is, you can even customize this as for the patient requirement. So that is the beauty of this technology, where you can even go with an orthopedic cast. And not only this, even it can be used as one of the drug delivery, say, applications. So you can use this technology to deliver the drugs in a more personalized dosages. So you have the as for the patient requirement. So you can say very well say personalized to his requirement. So for the drug delivery applications, so even it could be very well used for the drug delivery applications. And say the early users of this technology undoubtedly the orthopedicians. So the orthopedicians have been using this technology quite long time. Say that is right from the inception. This technology, the early user, the initial users of this technology undoubtedly orthopedicians. So that is because like where you're going to replacing either the hip replacement or any joints, finger joints or knee joints, um, or hip or pelvic or anywhere, say where you can replace these joints or the bones. So very well by making use of this technology. But I'm not going to discuss any orthopedic case study, but I'm going to discuss our personal experience with the dental implantation area, cranioplasty area, and the maxillofacial area, where we had some cases has been say work together that I'm going to discuss here. So during this lecture, this and next week we are going to conduct a dedicated program, and we are inviting all our collaborators to share their experience in all these cases. Then that is next week we are going to start that. So if somebody is interested from this group, you can also register for that course. You can hear right from the horse mouth, that is from our collaborators. But um, you know that we as a different domain people like engineers, and they are the people really they have the requirement and the end usage is done by them. So definitely their collaboration is very much needed here to establish any say application in this area. Why? Because you cannot independently or isolatedly work, and they cannot even independently or isolatedly work. It should be in a collaborative work. But anyway, I'm going to discuss these three areas, certain case studies, what we have performed along with them. I'm going to share that. And even not only restricted to these areas, like you can even say extend this to a biomedical device manufacturing. Biosensors can be fabricated, biomems devices can be fabricated through 3D printing technology, and microfluidic devices can also be for bioseparation and bioprocessing applications, and augmented tangible molecular models for research and education purpose. So even an anatomy class, these models can be also used as for the anatomy class for a medical student, or even DNA studies or molecular studies. So the biggest advantage here is, otherwise they used to work on a cadaver bones or a dry bones. So then how do they preserve? Then that's the biggest challenge for a radiologist or for an anatomy class who uses these cadaver bones to say. But here you can have these 3D printed models very well. You can use that application, and you can come up with several case studies or in the literature. So how this technology helpful for say solving a conjoint twin separation surgery, how complex it's going to be. You have a common neurons and common nerve system here, a lot of neurovascularity, commonality between these two twins, then how um, this surgery will made very simplified manner. So by making use of these 3D printed models, so then it will make the complex how the complex products has been simplified in engineering application. The similar logic will be extended for a surgeon to say simplifies the surgical treatment from complex surgical treatment to a more simplified treatment. Then you can make use of these models for that purpose. Or for the maxillofacial surgeries for the a sort of facial reconstructive surgeries. So these implantations can be very well done, or cranioplasty cases, or the finger joints, where you can make use of this technology, knee joints, or the femur bone, and you may have to maxillofacial reconstructive surgeries, or the prosthetics, or the orthopedicians. You can find tons of say case studies in this area. Uh, but the thing is, like, you are looking, then we need to have a very good partner to perform this, say, or to say establish an application. So definitely, it should be a collaborative work to work together, doctors and engineers, to solve these kind of cases. And let me come to the my next part of my presentation, that is, say, the 6 case studies, so that we have performed along with the doctors. So this is the first case study is a cranioplasty case study. So what we have done for this cranioplasty case study. So we have modeled and analyzed the cranial implant for the patient-specific cranial implant. So this is the case where we can see this is the portion you call that is a cranial bone. So you have the, the cranial, and you have lower jaw, upper jaw, that's a mandible, maxilla, and then you have this portion, um, uh, the bone that which protects your brain. So then that part, typically we call that bone region, is called as a cranial bone. So then a case with an accident case, where we need to design an implant, the cranial implant. So the challenge here is, like, the thickness of the skull is not a uniform. And then how do you ensure that you are going to get the best fitment of your implant versus the native skull bone of the patient? So then again, we need to start our journey by taking the CT images of the patient, and these are the images that has been taken from the Mimic software. So then we have a damaged portion here, and as we use the various tools that are available to, say, segment it and region grow it, and finally you can say save it as an STL file, and now we need to design an implant here that is that should fit to this the native skull bone. So during that say process, we need to take several say dimensions and several things, and ultimately our job is to so another challenge here is you have a cerebrospinal fluid. So that fluid will be, say, from the brain to the spine, it will be, say, sublime. So here, the one can understand the fitment, the importance of this fitment of this implant to the skull is going to be vital here. So how best you are going to design this implant versus your, say, the skull of the patient. So for that, so what we have done is we have fabricated this skull part separately, and then whatever maybe the design is the cranial implant. So it has been fabricated separately and tested for the fitment. And as we know that design is not as in a single step you perform. So then it will go in an iterative manner. So then similar way, we need to say come with several versions or several trials to come out with the best fitting of this implant to the patient skull. So that's what we have done this and we have published this in a journal. So if somebody is interested, you can visit this journal article also. And then coming to the next step is like say we need to say even check for um, your sometimes your say defects or the fractures may be beyond the midline deformation. So that case, it will become totally an asymmetric deformation or the case which we need to even do uh, our own algorithms to develop to reconstruct these surfaces. So, and then further, we need to say simulate the uh, the location of the fixation points. Means you have designed the implant and it should be getting fixed onto the skull of the patient, and then the location of these fixation points and the number of fixation points. So that is also going to play a vital role here. So your fluid, that cerebrospinal fluid. So you have the distribution, the pressure exerted by the fluid. So it should be uniform. So means your fixation points, the location of fixation points are going to play major role here to simulate and to optimize the location, and the number of fixation points also going to play a vital role here. Then these sort of tools will allow us to simulate and then come out with the optimal location and the optimal number of fixation points. And then, as I already said, like you have a limited say material choices with you to be used as an implant material. Say then PEEK is a one polymer, and polymethyl methacrylate, titanium 64 alloy is used here for the from the metal group. And we have say analyzed deformations and equivalent stresses for this say case of this implant. And this we have published this modeling and structural analysis of skull cranial implant behind the midline deformation in bioengineering and biomechanics. Say journal, if somebody is further interested, you can read that. And finally, you need to fabricate this implant, and it is getting fixed. As we know that the bone structure, if you observe here, so it's not a constant cross section across neither, or you have the inner bone maybe around zero point 0.7, 0.8 thickness, and the outer bone is around 0.5, 0.4 thickness. And in between, you have this, say, spongy kind of or porous kind of a bone structure. So then how do you, this is basically a sandwich kind of a structure where you have this sandwich kind of a structure. So nowhere you are able to manufacture through conventional manufacturing systems. So the 3D printing technology will enable you to make as a single setup or a single go. So you are able to make this skull, the skull bone or the cranial bone, and will be, say, biomimicking the patient condition. So this we have published in a, there is a one, as a unit cell algorithm meshless approach we have developed for doing this thing. And we have published in a medical and biological engineering and computing journal. So we are unable to explain everything in this 1 hour or 1.5 or 2 hours lecture. So then if somebody is interested, you can refer these articles. So it's there. in the journals. And so next case study is a dental case study. That's how this technology is helpful for fixing an implant for the dental application. So the um, the challenge for it, say the dentist here to say fix the implants. Say uh, so one case with 19-year-old boy, so he needs two implants here. You got two missed teeth in the molar, different molar positions here. So the challenge for the dentist here is normally a traditional manner. So they will take an impression from the mouth, right? Say, and that impression normally they take an POP material, it's plaster of Paris material. But here you have the challenge lies here as a inferior alveolar nerve. So that will say pass from that condyle and then touching this mental foramen again, it will say cover the other the condyle portion of the jawbone. And the thing here, so through from the impression technique, you will get only the outer surface information, but you never get this nerve information. So this nerve information, so then if you are not getting this nerve information, so then they may erroneously drill and then they may under drill or they may over drill, and sometimes there will be a chance to damage this nerve. So in that case, so the 3D printed models will help the dentist to plan or to rehearse in the surgery. So how much in depth he has to drill a hole to fix these screws or the implants, and say the what is the orientation and what is the diameter of the drill, the pilot drill, and then the finished drill they are going to say use that. So they can perform all that things, or even they can make a guide here to operate to fix the to drill a hole. Even they can make a guide or a template to guide for fixation of the these implants. So then you can give this model to the say dentist and let them do that rehearsal on this model. Say right, which you can clearly see this the alveolar inferior canal. But this is which we have done almost like say 12, 13-year old. But now you have 100% transparent materials. So through a DLP based technology, so you can see through almost so 100% say transparent materials also available in the market. Like say even you can make use of that, and cost is also not that much like earlier days, but the cost is also reduced with the DLP or SLA based desktop printers. But we don't have that facility. Then we have used an FDM based technology, but still now you can make use of these transparent materials which you can even see through about that now. So you have such an opportunity here to say sit with the say dentist, and then you say it is an opportunity for them. So they can do whatever they need. So they can perform that sort of mock surgery or the say trial surgery on these models, and then come out with the best design of the implant. Then what should be the size of the implant. Normally they will get a standard sized implants maybe from Jimmers or other companies. They purchase and they fix it. But definitely you can have a customized solution through a 3D printing technology. You can even print that implants say, and then mostly it will be made out of titanium alloy. So then you can make use of this 3D printing technology, and then you can say directly based on that, say the mock surgery or the conclusions they have done based on that surgery made initially done through the models, so that has been taken from the patient, and then based on that, so they can directly go to operation theater, and then they can say fix that implant as for the patient condition. So they can fix that implant. So this is what where your a dentist can make use of this technology for fixation of the implants, the right place, right position, and the right uh, the, the precision levels of the surgery will be improved, and then in the templates can also be say printed here, and then they can use it during the surgery. So this is what where this technology is helpful for the uh, dentist for fixing the implants or designing, fabricating the customized implants. And then next case study is the mandibular distraction osteogenesis case study. So you have a surgical procedure called, say, they use a device called a distractor, and osteotomy or osteogenesis means so they cut the bone and the bone will grow. The bone will be having its natural growth, and depends on the age, gender, it will vary. And then what they do is so they do say cut the bone, and then they use a device called a distractor to guide the bone growth, means the twisting and then the stretching, all that will be say guided through this device. And then here is the basically a reconstructive surgery. This is for the mandibular reconstruction surgery. So she is 8-year-old patient who needs, which you can see there is a facial deformity. So by birth she had this problem. So which we can see the normal opening is 5 to 6 centimeters. A healthy person can open the mouth, and she could not able to do that, and which you can see there are a lot of the facial region, so the abnormal growth of the bone and the facial say deformity, and which you can see in the other view. This is the facial deformity, and which we need to start this with taking the CT data of the patient. So then it has been reconstructed, and further it has been taken the mandible and the maxilla portion. So then this has been done in a mimic software. Reconstruction has been done and saved it as an STL file, and further it has been printed by using 3D printing machine. And then what 3D printed models are going to help you out here is same. Next, they need to say, this is what I'm talking about. There is a distractor. This distractor. So you have the internal configured or the external distractors. So based on the condition of the patient, then they can fix it either internally or externally. So this distraction, so the internal mandibular distraction, it is here, and it may be along the mandibular bone, and say this will be so there will be a screw kind of a arrangement here, so that say maybe one revolution 1 mm advancement or something like that. So then you can be able to calculate those vector values through this models. So that has been say derived from the 3D printing, and then that's based on the patient condition. So then you can say calculate those. Say I will try to show you in this model. Say you have this um, model. It has been generated from the patient data, and which we can see it's supposed to be a semicircular arc if it is a healthy patient and the healthy person. It should be, but where you can find this say abnormality here in the bone growth, and this is what it means. It should be twisted here. So then, not only that, you can see this ramus height of the survived one to the defect one. So this is very shorter when compared to other side of the ramus height, and it should be stretched, should be lengthened, and it should be twisted. So then how much it should be twisted and how much it should be lengthened, and the what is the revolution of that screw? It should know. Say take that thing into say that sort of calculations, and that sort of conclusions will be done based on this model and this condition of this patient. So then you print this and sit with them, and then they will very well plan the device and the surgical procedure. So based on this patient condition, and this is the initial condition of the patient, and this is the say which you can see still this is during transformation, and we can see this distractor has been kept it here, but still you may wonder why this is not say 100% perfect. Means so you have the bone growth will be the up to teenage now say the bone growth will be say predominant, and then this has been overcorrected as of now. This case, so it has been overcorrected, and once she turns into say 19 18 19 year old, so it should be finally corrected. So in this way, so your 3D printed models are helpful for say planning, designing the devices for assisting this surgery. So it will be done in that way. So this is the one level of application. And the next level of application we tried is like say, this is one of the amyloplastic fibroma of mandible. This is one of the defects or the case they can perform. So this otherwise is a cancerous bone reconstruction. So which we can see this portion. So where from the X-ray image. So this is a say here how you are going to make use of the 3D printed models here. So definitely you take any CT data of the patient and further, so you can print this model. So, and even in the design itself, so you need to say remove that portion anyway. That's a tumor or a cancer or whatever it is, which we need to remove this portion of the say the lower jaw here. And once you remove that, and it should be augmented with the implant. So then how do you design that implant? So then again, you can make use of these software tools to design this implant. So you have, say, what you call, you have the defect side, and then you can have the survived side. So you can take an say mirroring option, mirroring image, and then you can say copy that survived to the defect side the same, assuming that it's the symmetric, and then you can say copy the same thing from the survived to the defect side, and how much it should be done and what is that. So it is very well done by making use of the software tools to assist you to do that. And then how much we need portion we need to remove that, and even you can make a model, and then you can even supply to the surgeon and let them do rehearsal, or let them cut that say unwanted tumor or the cancer bone, whatever it is. So it should be say removed, and then they can say do all that stuff right on these models, and you can design very well for the say further. So you have cut this portion, and then which we are trying to say augment with an implant. And again, we need to provide the nerve relieving, because you know that nerve will be passing from this condyle and it is going, and we need to provide the nerve relieving for the through this implant, and it should come from the other side. So then what is the design of this implant? So again, you want to make it as a lightweighted structure, and this is the design, and further it has been printed initially with a polymer based printer. And is it the ideal design so to come out? But definitely you can have a lattice based design here to serve two purposes. One maybe the lightweighting of the bone, the implant, and another maybe to improve the osseointegration between your say implant to the bone. So that is the always there. So then you can say get the advantage of say lattice based design here. So you can say come out with the lattice based design rather than a standard solid design. So then we suggested different designs to the say the surgeon to say decide like which kind of design they are interested to say in order to have the better osseointegration also keeping in mind, right? So, and then which we are able to fabricate this in a titanium 6-4 is the material used. And then you may get doubts, sir, why those are here, why it has been not implanted. But this was our first attempt to implant, but we have stuck up with certain procedures like the ethical clearance or the certifications and other issues. Then we stuck up, but they don't have much time, and then they have used the conventional method, say, to at least what we have done. We have supplied these models for, say, fixing these plates onto these models during the surgery. And this is the during surgery, they have removed that, and they've done the conventional method, the bone grafting uh, technique they have used to, but still they are not convinced with the conventional surgical method. Why? Because it has not, say, happened. They are not comfortable with the level of the surgery, the outcome of the surgery. And then they have again approached us, can we reopen it and redo it by using the implantation with the implanted thing. Why? Because we have succeeded in the next case to implant the implant into the next case, that is the TMJ oncolysis. So then this is our successful attempt, and that too, this is a TMJ oncolysis is supposed to be the complex surgery. If you ask any oral maxillofacial surgeon, so then he will tell you about the level of, say, complication that are involved in this TMJ oncolysis kind of a surgery. So this is basically to this is the case description. So she's a 20-year-old, and she had a problem of fused joint. Here, this TMJ is the joint which joins your lower jaw and upper jaw, and you have a lot of nerve system also here. So it's very complex surgery as far as the oral maxillofacial surgeon is concerned. So then, how do you say detach that fusion of the joint, and again freshly you are going to, say, redesign that joint that is as for the patient say condition and the anatomy, the geometry and the dimensions and so on. So then luckily only one side of this you have two joints, right? So you have two joints, one is left and another is right. So you have these two joints, one is got fused, but another one, God has given a hint that the other one, the survived one, is then we thought that we can copy that same dimensions once you, say, dismantle or once you detach this fused joint, and trying to freshly start designing the say joint for this patient. And this is what I'm talking about. So this got fused, this lower jaw and upper jaw, and this TMJ, this has been fused, and which you can see that joint is responsible for easy articulation of your say jaw. So it should be free from the constraint. Means it has been suffused, but it should be free. Then only he or she can, say, easily articulate the mouth, opening of the mouth, and normal opening, biting, chewing has been done. So because of this, she could not able to open her mouth. Even she used to manage with the fluids, and then so on. So then, which we need to what we need to do first, we need to say dismantle this fusion, and then freshly we need to design and fabricate a joint for her. And initially it should be which we can see here from the model very clearly. You can see that how it has become an integral part of the joint. So it should not be like this. So it has been fused, and it both will become an integral part. So anyway, so here which we need to do distraction osteogenesis procedure initially to stretch forward this bone. So in order to get aligned this thing, and which we can see this distractor has been used to say those kind of things can be calculated here. The vector calculations done through this patient specific models, and then it should be stretched forward, which we can see during the transformation. So this is going to happen during the surgery. Like they can very well plan how much it should be brought forward. So maybe 19 mm, 21 mm, like that. So one side 19, so 21 the other side. So like which we can come out with that conclusion. So based on this patient condition, and then this has been say and this is during the surgery where you can see the distractor has been placed, and this is a transformation like say the bone has been say stretched forward initially 2 mm, 3 mm, 4 mm, and further has been stretched. So this is the condition of the patient. This is the, before the surgery, and this is during the transformation after the I think this, which you can see now, it got aligned. But the thing, the major thing is that we need to say perform this TMJ, say this joint design, which we need to say this is what I'm talking about. We need to fuse this, release this fusion of the joint that we need to do it initially. And then for that purpose, where we, as I already said, we have used the survived side as we say assume that as symmetricity, and then copied this from the survived to the say defect side, and this is the design, and this is initially printed on a say a polymer based printer, and this FUSA say component also, which it has been say assumed that the survived side to the defect side, and this is the design, and this is the 3D printed one, and this is made out of the biocompatible material polymer that has been printed. So that is with the 3D printing machine, and say from the maxilla side. So you have a zygomatic arch and then this fossa component. And from the mandilla side, mandible side, you have this condyle portion, and then this is going to become the joint like this. Initially, it has been printed in the polymer-based say printer, 3D printer used to print this the model as well as the implant, designed implant, and checking for the fitment like this. And finally, it has been printed on a titanium 6-4 metal 3D printer. And even we have designed a guide for, say, fixation, easy fixation for the surgeon to fix this implants into the, say, the bone during the surgery. Yeah, this is what. Then we have designed a guide for them to so to fix the implant onto the bone, the jawbone of the patient. And this is during the surgery. I was very well there, and the surgical team and my PhD scholar and my collaborator, Professor Ryan Gibson from Australia. We had a collaboration. We have a project, and then we invited him for that discussion. And during that, we fixed this the surgery, and I was very well there inside the surgery too. Yeah, which we can see. This is the once she had for the past 21 years, she has been surviving that fusion of the joint, and once it has been released, now it is say 4 to 5 centimeter opening of the mouth. We can see the opening of the mouth, right? Um, yeah, this is during the fixation, like this. It has been fixed from the say zygomatic arch side, and these are the screws. It has been fixed from the maxilla side, and this is from the mandible side, which it has been fixed with this screws. So this has been successfully implanted. This, and you can see this patient now. She could able to open her mouth now. Normal opening and normal biting and normal chewing has been attained. So like this, she has been surviving for the 20-21 years, and now she had a better societal life. So definitely, if they are having a certain say surgeries which are long-term pending or complexity involved in the surgical procedures, so definitely 3D printing technology may able to resolve those kind of complex surgeries into more simplified surgeries. So that's what where you can say collaborate with the hospital people to say solve these kind of complex surgical treatments. And then I have last case study. This case study is a vessel osseo integrated implant. So again, 3D printing is going to play a vital role in developing a patient specific implant or indigenously development of the implant. Why I'm saying this is so there's a male patient who met with an accident, and he lost the 5 teeth along with the partial bone damage has been happened, and cannot fix all the teeth in a conventional way. Why? Because so if you have the standard implants that are available in the market, so then five should be, and then you don't have much support with the bone. Why? Because the partial bone has been also damaged, and you don't have the provision to fix the conventional implants here for this case, and you have to have the nerve relieving option, and of course the density of the bone is not uniform, and the angle of the teeth placement and so on. So because of this the conventional methods are not worked out. So then definitely, and that if you see this is in what you call an asymmetric fracture. So we are not expected to broke his thing in a more symmetric way, that is for ease of your designing, no, right? So then this is what where we need to based on the patient condition, the fracture, then we need to design an implant. And then here say I'm talking about the conventional say implants which they anyway they could not accommodate here these implants and fixing the abutment and so on, but that is absolutely not possible through the conventional implants. And then we need to develop an indigenous implant for this case to fit this implant here, and the abutment and the teeth should be fixed here. So this is the entire thing which we need to, based on the patient design, the fractured say dimensions, we have designed an indigenous customized implant. So the base plate and the connections and the abutments, everything has been designed. So and then which we can notice that it is an asymmetric fracture which should match your design of the implant. So then it has been done accordingly, and we have tested for the failure of this implant. Then through an FEA analysis, FEM analysis, we have done that, and then even we check the fitment of this say implant in the software, whether how it is getting fitted, let's say whether it has been fitted properly or not. And then we have checked all that, and once we have validated everything, and then initially we printed this implant and the model through a polymer based desktop based printer. It's a small desktop based printer with a PLA material, just we printed initially, and giving it to the surgeon, like and let them do a rehearsal on this surgery, then where they have to say made insertion, and then insertion of this implant should be done onto this the bone of the patient, and then ultimately it may be coming with this at least four teeth has been accommodated, so it's going to be like this. So and then we printed this implant, the designed implant. So after treatment testing and after a finite element analysis, and finally we have come out with this fabrication of this implant. So that has been printed in titanium 64 and a metal 3D printing machine. And these are the supports, support structure. And after removing that support structure and performing the autoclave and that say sterilization process and that regulations normally they follow for implantation purpose, and then as for the regulator suggestions or the standards, so it has been done, and this is after all that has been done. Now this, which you can see, this implant has been fitted here, so which we can see initially this is a snug fit, like where initially it has been, and then final placement of this implant here into the patient mouth this way. And this we have published in one of the reputed journals called Rapid Prototyping Journal. This case study has been published. If somebody is interested for that information, you can refer that article. So this is the post surgery the image. So this is the placement of the implant. So you can see this, and top of it you have this. The teeth has been fixed, the four teeth has been fixed. So in this way, this 3D printing technology is helpful for even designing an indigenous and the patient specific implant. So you cannot find a standard implant like this dimensions. Why? Because based on his condition, the fracture, and it has been, say, designed, fabricated, and fixed. And then in this way, you can find several situations where a surgeon needs a customized patient specific or patient matched say implants are needed. So then 3D printing technology will help them, right? Say in some cases you may have abnormal growth of the tumors, then it may become very complex surgical treatment for a surgeon to operate. And then you can, apart from your CT data and further, you can make the models and then make use of those models for, say, aiding the surgical procedure. And you have several cleft cases by birth. You have certain cases, and then even further, it could be done here by making integrating 3D printing technology, and some accident cases, but the head injuries, so some severe accident and trauma and then emergency cases, sometimes you may not be take up these cases. Why? Because you may not be able to supply these models as they demanded, maybe 1 hour, 2 hours, or maybe less than that if it is emergency case. But we need to know our say capabilities and the technological limitations or the any software limitations which we have, means what they are expecting from you, like it is an emergency case or any other situation where we need to accordingly say react and collaborate with them to take up the case and further to say resolve it, right? So that is our experience through the 6 case studies which I have presented here. And the so far we are discussing, okay, 3D printing technology has been replaced a bone or a joint or a prosthetic. Okay, fine. But can it be replaced an organ which it has been, say, regenerated by using 3D printing technology? Can it be, say, implanted into the patient body? So that's that's going to be the future direction. So far, you have a man-made material like, say, titanium or cobalt chrome or 316L, or maybe it may be PMMA or a PEEK, or it may be say you may have other, say, ceramics, or say bioceramics, biocomposites, or anything which has been man-made or synthetic materials. But but future may be differently. It's going to be a natural material undoubtedly. So what is that natural material? So it may be the living cells of the own patient, maybe going to be the material that you're going to print it. So then you may prepare a collagen, you may prepare a cell ink. So which these cells has been taken from the living cells of the own patient, say organ where you are targeting it, maybe a piece of that tissue or the cell might have taken, and that cells might have say incubated in a incubator, and further it has been cultivated, and then it has made a kind of a ink or a cell ink, or basically this material is totally a natural material, or maybe it's not a synthetic or the material that previously we were discussing, but you prepare that and then you jet it or you print it, you grow it, and further again you put back into the organ, means maybe replacement, maybe repair of that organ you are targeting to do that. So again, we need to say start with this journey with say again with an MRI data, and then bioprint collagens in human heart cells, and further again it is getting putting it into the patient. But it seems fine, but it may not be that much easy. That so far you are doing it in terms of 3D printing medical application. So this organ printing is definitely, if you summarize, so what is this organ printing is all about? So you have to extract a cell from the own patient body. So you extract the cells and you add proteins, nutrients, or you do a cultivation. You multiply these cells into thousands or millions or billions of cells. So by multiplying it and growing it and incubating it in an incubator, and you form an organ. So your cells has become, say now as a tissues, and further now it has become say organ. So that can it be directly fitting it or printing it or placing it into the human body in terms of your organ replacement or the organ repair. So can it be done, or there will be several challenges here, whether directly you evaluate this say the cultivated cells, or the it has become the tissues, or whether these tissues are a sufficient mechanical property or sufficient say neurological or any property that a native organ is having, and the functionality of the native organ that it is performing, can it be done the same thing which it has been say prepared, and it has been generated, and it has been, say again, putting back into the patient a human body. So whether it's going to uh, work with the same manner that the native organ is there. So that is the $1 million question. Like say the mechanical properties, the physical properties, or the biological properties, all that is it on par with the native organ? So that is a huge challenge for these kind of practitioners. They already put forth some developments in this direction, like say the bladder has been already regenerated and it has been successfully say implanted, and skin is the another tissue that people has already tried and say um, replaced, and the blood vessels is also people have successfully done. But if you talk about the complex organs like lungs or heart, liver or kidney, so definitely they have to address several challenges, and then maybe the time may be the answer for these challenges and the developments that are happening in the recent times. So we hope that we are able to successfully transplant or successfully repair any complex organs, maybe as of now it may be not, but maybe we can hope in the future, maybe down the lane, so 10 to 15 years, we can find a lot of breakthroughs in this direction. Definitely we hope that one day we can see that it is getting printed and it is getting mm, up to the standards that what we are expecting. So definitely one day will come that we can use this 3D printing technology for the even organ printing and organ transplantation and replacement. So with that, I have concluded my talk, and before handing over to Dr. Manjaya, so then let me summarize what I have done for this session, almost like 2 hours. It is touching. So we have started with the medical scanning technologies, CT, MRI. That is going to be the start point of this practice, the medical 3D printing practice, which should come from the medical imaged data, and further it should be processed by making use of any medical image processing software to process those images and reconstructing those images, and finally it is compatible or the readable format for the 3D printing, which we need to brought that data in that thing. And then we have discussed biomaterial, the characteristics of the biomaterials, and then the state of art of biomaterial that can be printable through 3D printing technology. And we have discussed some scope of the virtual models, but virtual models not always be the solution for the complex surgical treatments. And definitely we have to have a physical diagnostic models or physically printed pre-planning surgical models. I hope I have conveyed these applications through my case studies. Maybe for planning the surgical procedure, or customizing the implants or the prosthetics for the patient-specific, patient-matched implants, prosthetics, and the medical devices like implantable, non-implantable like tools, guides, templates, and supporting devices. Even it could be extendable for the arm braces, knee braces, and etc. And at last, we have discussed the state of art of this say tissue engineering, organ printing, and bioprinting. So the future technology that we are going to evident very soon, maybe near future, or some initial steps has been done, and some simple tissues or the organs has been already successfully implemented. Before I conclude, and I would like to acknowledge a few people here. Definitely, without their support, the requirement should come from the surgeon or the hospital side, and again the end users also the hospital people, the surgical people, the surgical team. Then we had a very good surgical team to collaborate with us. So we have Dr. Shekhar Reddy and Aditya Mohan from Panniya Dental Science and Research Center, Hyderabad, for the oral maxillofacial and craniofacial surgeries. And we have Dr. P. Mahesh from Narana Dental College for the dental related case studies, and their PGs also is highly acknowledged here, their support while performing these case studies, which are presented here in the form of 6 case studies. And we do acknowledge DST and SCRP for their financial support to assist these research on the case studies. And last but not the least, my UG, PG, and PhD scholars, which you might have noticed these citations of the papers. So this is the work of at least 2 to 3 PhD scholars work, namely my first PhD scholar who worked under me with Manmadachari and Santosh, and the cranial cases done by Fanindra. So these are the 3 PhD scholars, and some of the MTech additive manufacturing people has been we have given a part of this work to PG and UG dissertation and the their project works. So we'd like to highly acknowledge these people who directly or indirectly involved during these 6 cases which I have presented here. And of course, these are some of the facilities. Anyway, the next session will be on the after half an hour break, 11:30 onwards. So we are going to give the demo on all these facilities, the metal, including metal 3D printing facility. Also, we are going to give a demo on these facilities we have at our lab. So I hope I have done from my side. If you are having any questions, yes, I am very happy to answer, take up those questions and the suggestions or your comments. So I'm very well answerable to those questions. So it's over to you, Mandigar.
Thank you, sir. Thank you once again for giving a vast information on this medical applications of 3D printing and all, how to scan the patient, which is the part like the CT scanning, MRI scanning, and also giving a different biometals can be used in this medical applications, and also the real time examples with many case studies. You had given a vast information to the participants. Thank you, sir. Thank you for giving your knowledge, sharing your knowledge to the participants. Participants, if you have any queries, please unmute yourself and ask the queries, or you can put it in the chat box also.
Thank you, Dr. Ranganathan Garu.
It works, sir. Wonderful. It was very nice looking at all the cases. So, what was the polymer used for the TMK implant for the glenoid fossa to stimulate the glenoid fossa, simulate the glenoid fossa?
No, this is the PC only with a bio grade PC.
Polycarbonate with polycarbonate. Okay, fine. And also, can I ask you one more question, sir? For soft tissue, in case you were to have, as you mentioned, for putting the stem cells or the mesenchymal cells, if you have to have a soft tissue cover, something that's flexible, what would be the best material that you can use?
Then you can try with an epoxy, which is biocompatible epoxy resin, which is done through an SLA-based system or a DLP-based.
Okay. Anything that would be resorbable over a period of time?
We do have a certain resorbable materials which is done through an epoxy-based system. Yeah, it will be a resorbable materials also there. Yeah.
Fine. I'll get in touch with you later after this course is over, sir. Thank you so much. Really nice. I was very impressed.
Thank you.
God bless all of you all and wish you all the best in your journey ahead. Thank you. Thank you so much. I've enjoyed this course. Thank you.
Can you please introduce yourself, sir? Actually, for the sake of other participants, actually.
Okay. Good morning, everyone. I am Dr. Rangnath Nayak. I'm an oral maxillofacial surgeon. I've been practicing for the past 35 years. I'm a teacher, professor, head of department in a college in Belgaum, Karnataka. I passed from Nair Hospital Dental College in '84, and I have been. We have a good setup here. We have one of the country's best research labs as far as soft tissue, stem cells, everything go. It's called a Central Research Laboratory. You can probably Google it. You'll find out. We are noted as Center of Excellence, and I think we have established in 2013. I'm sorry, 2013. Yes. And in the 7.5 years, we have conducted more than about 2,200 studies. Postgraduates, PhD scholars, research scholars from all over the country come down here for their research work. And we have a nice setup. Probably I like to invite you all to come over sometime and have a look at it. And we would also
definitely will. Yeah, we'll have a collaboration with you. And then if anybody is interested, you can, from the participants also.
So thank you so much. I've really enjoyed this course, though it was a lot of engineering, a lot of drawing, which I've never been used to. I tried my best, but you all made it very simple. And you had appointed one Dr. Rakesh Sankineni to look after me, to be my handler. He's done a great job. He's been very patient with me. I'm really impressed with the work that you all are doing, and I really wish you all the best. Thank you so much. Thank you. Thank you, sir.
Thank you, sir.
Hello, sir.
Yeah.
Hello.
Yeah,
hello.
please.
Yes, sir. Myself. Hello, sir.
Yeah, please.
Yes, sir. Myself, Baban Suryatal from PDA College of Engineering, Pune.
Okay.
I would like to ask, sir, what is the cost of liquid-based, that is DLP-based stereolithography system?
Yeah. So the liquid-based stereolithography, desktop nature, you can get it around 3 to 4 lakhs. So now the cost has been come down. So you can get a printer with the DLP-based epoxy transparent material around 3 to 4 lakhs from Form Labs. Form Labs, US-based company. So you can
Okay.
get around 3 to 4 lakhs. You can get a decent machine. Yes.
Okay. 3 to 4 lakhs in this.
3 to 4 lakhs from the
Okay,
Form
that
Labs.
is we are planning to purchase that is set up for our college, sir.
Okay. Yeah, 3 to
Okay,
4 lakhs. You can.
okay, sir. Thank you very much.
Okay, thank you.
And sir, very nice session, sir. Very nice and informative session, sir. Thank you very much, sir.
Thank you. So then, if you don't have any questions, and one more thing, if you are interested, probably you may be knowing it. I'm not sure. And we are again inviting you for the next course. Maybe try to share my screen. No, anyway, I think no. We have
Startup session
another
only it is
Atal.
there.
Yes. Yeah. Are you able to see this screen?
Yes, sir. Yes, sir.
Yeah, we are again inviting you for the next course from going to start from December 14. That is on medical applications of 3D printing, where our collaborators are going to come and say discuss the elaborate from the medical people, means the surgeons also going to say participate and going to give the lectures. 50% or more than 50, 60, 70% lectures will be done from the hospital side, our collaborators. So again, once again, we are inviting you, and we are say requesting to pass on this message to the to your friends. So December 14 to 18, that is exclusively on medical applications of 3D printing. So again, you can go to the Atal and then you can register for this course also. And kindly I request to pass on this message to your colleagues and the students, right? So again, I'm requesting you for this say registration for this course if you are interested. Yeah. With this, I would like to say conclude this session, and yeah, so it's over to you, Manjaya. Then I will be signing off. Hello.
Some queries in the chat box.
Okay. Yeah.
Yeah.
Can you
One.
read out?
Yeah. Dot .skp and dot .dae files only downloading, which are not opening properly in Cura. They are asking.
No. You ask Rakesh. Rakesh is there. Rakesh or Srikanth. Anybody can answer this.
Hello, sir. I'm here, sir.
Yeah. Please.
Yeah.
Can you address that question?
Dot skp and dot a files only downloading, which are not opening properly. Sir, these G Prashant, sir, these formats we too don't know. Only we will work on the STL and STP and SVG. If it is, if you are working in the Tinkercad, those are the files we are importing and exporting into STL. These files, I will personally text you, sir. I will solve. I'll try to know about these things, and I will meet you. Okay. Sir, whenever, as like some suggestion came from Rangana sir, thank you very much. Whenever you are converting from the online to this SKP and DA to STL file, there might be a loss of data. So I suggest you not to do that one. But if it is any another software is available, then try to develop them into the STL format. That is a good option, like to convert them in the online to STL, but the file size might be the clarity, like the resolution, the STL triangles may be lost. So that is one of the error if you are working on the online like these things. Okay, sir, I will text you personally. The Prashant sir, these two file formats are unknown to you, us. Like we don't work on these things. Even in the Blender, we worked on the Blender, Mesh Mixer, and Maya and Mesh Lab. These things we are usually work, but we will deal with the OBJ, STP, STL, and SVG files. Okay. I hope you are clear. Thank you, sir. Thank you very much. Okay, sir.